Today we are going to learn about optimizing k-means with elbow method and silhouette score. We'll explore how to determine the optimal number of clusters for k-means, enhancing the algorithm's accuracy and effectiveness.
Welcome to our educational video on optimizing k-means with elbow method and silhouette score. In this session, we will delve into the importance of determining the optimal number of clusters in the k-means algorithm. This is critical for ensuring the effectiveness and accuracy of your clustering results. We'll begin by exploring the basics of k-means clustering, followed by an in-depth look at two methods used to optimize the number of clusters, the elbow method and the silhouette score. By the end of this video, you'll have the skills to apply these techniques to your datasets, ultimately improving the performance of your clustering analysis. The elbow method is a popular technique used to determine the optimal number of clusters in a dataset when applying the k-means algorithm. This method involves running the k-means clustering on the dataset for a range of values for number of clusters and computing the sum of squared distances from each point to its assigned center, known as the inertia. The goal is to identify the elbow of a plotted graph that shows inertia versus the number of clusters. The elbow point represents the optimal number of clusters, where adding another cluster does not significantly improve the model's performance. Understanding this concept is crucial as it ensures that the k-means algorithm is neither overfitting nor underfitting the data, providing more meaningful insights and enhancing the overall effectiveness of the clustering analysis.
To plot the elbow curve, we need to have a range of values for k, which is the number of clusters. Typically, this range is chosen based on the dataset size and nature. Start by importing necessary libraries such as NumPy, Pandas, and Matplotlib, along with k-means from scikit-learn. For each value of k, fit the k-means model to your dataset and calculate the inertia. Store these inertia values and plot them against the respective k values. The resulting graph is known as the elbow curve. The elbow in the graph is the point where the inertia starts to decrease at a lesser rate. This indicates the optimal number of clusters. Visual aids, like highlighted elbow points or annotations, can enhance the understanding of the plot. This entire process not only aids in choosing the correct number of clusters but also provides insight into the data's underlying structure.
The elbow point in an elbow curve is crucial for determining the optimal number of clusters. It is the point where adding more clusters yields diminishing returns in terms of reducing the inertia. This point reflects the best trade-off between model complexity and performance. Identifying the elbow helps to avoid overfitting, where too many clusters may lead to over-segmenting the data, capturing noise rather than useful patterns. In real-world datasets, the elbow might not always be distinctly visible, requiring a careful balance of domain knowledge and statistical judgment. By focusing on the elbow point, we align the clustering process more closely with the actual structure of the data, ensuring that each cluster is meaningful and representative of a distinct group or pattern within the dataset. The silhouette score is another powerful metric used to evaluate the quality of clusters in a dataset. It measures how similar an object is to its own cluster compared to other clusters. The silhouette score ranges from -1 to 1, where a score close to 1 indicates that the data point is well matched to its own cluster and poorly matched to neighboring clusters, suggesting a good clustering configuration. On the other hand, a score close to -1 suggests that the data point may have been assigned to the wrong cluster. The silhouette score provides a more comprehensive understanding of the cluster quality compared to the elbow method, as it considers both cohesion, how close the data points are within a cluster, and separation, how distinct the clusters are from each other. Understanding this score enables data analysts to validate the clustering results and ensure that the number of clusters chosen is optimal for their specific dataset. Calculating silhouette coefficients involves determining the average distance between a data point and all other points in the same cluster, and the average distance to points in the nearest cluster. This is achieved using scikit-learn's silhouette_score function in Python. First, ensure your data is clustered using k-means or another clustering algorithm. Then, pass the data and the predicted cluster labels to the silhouette_score function. The resulting value provides insight into the quality of the clustering. A high silhouette score indicates that the clusters are dense and well separated. By analyzing these coefficients for various numbers of clusters, we can better understand the structure of the data and make informed decisions about the optimal number of clusters. This process is crucial in applications where the accuracy of clustering can significantly impact the results of the analysis.
Interpreting silhouette scores is an essential step in validating the clustering results. A high silhouette score indicates that the clusters are well formed, with distinct and dense groups. Conversely, a low score might reveal overlapping clusters or outliers that need further investigation. By examining the silhouette scores for different numbers of clusters, we can identify the optimal clustering configuration. This score becomes particularly useful when compared with the elbow method, as it provides a different perspective on the clustering quality. While the elbow method focuses on the inertia and reduction in within-cluster variance, the silhouette score offers insight into the cluster's cohesion and separation. In practical applications, combining both methods allows for a more robust analysis, ensuring that the chosen number of clusters accurately reflects the data's inherent structure. The elbow method and silhouette score are complementary techniques used in determining the optimal number of clusters. While the elbow method focuses on the inertia or within-cluster variance, the silhouette score assesses how well separated the clusters are. Each method has its advantages. The elbow method is straightforward and easy to interpret, while the silhouette score provides a more comprehensive evaluation of clustering quality, considering both cohesion and separation. The choice between these methods depends on the specific dataset and analysis goals. Often, using both methods in conjunction provides the best results, offering a balanced view of clustering effectiveness. In practice, the elbow method can quickly highlight the potential number of clusters, while the silhouette score can validate and refine those choices, ensuring robust and meaningful clustering.
Let's put theory into practice by implementing k-means clustering in Python using a real dataset. We'll start by importing necessary libraries such as pandas for data manipulation, NumPy for numerical operations, matplotlib for plotting, and scikit-learn for the k-means algorithm, elbow method, and silhouette score. First, load your dataset into a pandas data frame, and execute the k-means algorithm for a range of cluster values. Plot the elbow curve to identify the potential number of clusters. Then, calculate the silhouette scores for these clusters using scikit-learn's silhouette_score function. By analyzing these results, you'll gain hands-on experience in determining the optimal number of clusters. This practical example showcases how these methods can be applied to real-world data, enhancing your understanding and ability to implement clustering analysis effectively. The integration of both methods provides a comprehensive approach to cluster analysis, ensuring accuracy and relevance in the results. Determining the optimal number of clusters can be challenging, especially with complex or high-dimensional datasets. One common difficulty is identifying the elbow point if the curve does not show a clear bend. In such cases, relying solely on the elbow method might lead to suboptimal clustering. Another challenge is interpreting low silhouette scores, which can indicate overlapping clusters or outliers. To address these issues, it's advisable to use both the elbow method and silhouette score together, as they offer different perspectives on clustering quality. Additionally, domain knowledge and exploratory data analysis can provide insights into the data structure, aiding in the selection of appropriate clustering parameters. By combining these strategies, you can overcome the challenges of determining optimal clusters, ensuring that your analysis is both accurate and meaningful. Implementing best practices in cluster analysis is crucial for achieving reliable and insightful results. Start by thoroughly pre-processing your data, ensuring that it's clean and normalized, as this can significantly impact the clustering outcome. Choosing the right distance metric, such as Euclidean or Manhattan distance, is also vital, as it affects how the algorithm perceives the proximity of data points. Evaluating cluster stability through techniques like cross-validation can further enhance the robustness of your analysis. Moreover, incorporating domain knowledge allows for more informed decisions when interpreting clustering results. Finally, continuously learning and adapting your approach based on new insights and advancements in clustering techniques ensures that your analysis remains relevant and effective over time. In conclusion, we've explored the importance of determining the optimal number of clusters in k-means clustering and how this can significantly impact the accuracy and effectiveness of your analysis. By understanding and applying the elbow method and silhouette score, you can make informed decisions about the number of clusters that best fit your data. These techniques provide complementary insights, ensuring robust and meaningful clustering. We encourage you to practice these methods with your datasets to gain hands-on experience and confidence. As you continue your learning journey, explore additional resources and stay updated with new advancements in clustering techniques. Thank you for joining us in this educational session, and we wish you success in your data analysis endeavors.